ice cream, little monkey balloons? No? So this is the last session, and we finish with Monsieur Tom Matcha. You still have time to go into the LinkedIn competitions. If you still want to do it, please do. There is some nice prizes. So a little bit about you, Tom, and then we can kick off. So Tom, you are the head of data with 12 years of experience in the industry. For 7 of those, you run 2 machine learning startups. 1 to help game company personalize user experience, and another one to automate product analytics. So now you're currently establishing the data team at Ghost Media, a social betting company. And you're going to talk about method and philosophy for effective data science. So please, everyone, put your hands together to give a warm welcome to Tom.
Thank you very much. Hello. So I've slightly abbreviated the title of my talk, just a bit more. Mic problem there? Give it a go. Here you go. Hello, hello, hello. Okay. Maybe it's okay. Maybe not. It seems to be dropping out there. I'll keep this handy just in case. So, title of the talk, Data Pseudoscience. The idea is that I'll be proposing some reasons why data scientists such as myself struggle to add value and discussing some tools and principles that I found to be effective over my time in the industry. My goal here is really to pack as many ideas as I possibly can into a talk, and I hope that at least some of those ideas will be valuable to you in your day-to-day practice, presuming that everyone here is working in data science as it stands. So the talk is split into 2 parts. Part number 1, failure of science. It's really based on my observations of working in this industry for now 12 years and condensed experience talking to of friends and colleagues. My claim is that the vast majority of organizations that are employing data scientists are getting a positive return on investment, and not even close. And this is certainly inspired by my own experience of just being totally ineffective, trying to deliver any sort of value for the companies I've worked for, and finding that quite frustrating. And it's really not feeling everywhere. There are companies we've seen speaking today who are able to extract a lot of value out of the data science process, but in the vast majority of companies I've been working in, there have been problems like misunderstandings of roles, poorly specified goals, and just an inability to actually produce anything effective due to the constraints of the problem that we're in. So I've got 3 quotes which I feel underpin the problem, and then we're going to sort of what I think is actually beneath the surface of those problems in particular. So this is from a blog post that I read recently, which has been doing the rounds, called "I've been employed in tech for years, but I've almost never worked," which I thought was particularly provocative. But this one quote from it stood out for me. A former colleague was hired a year ago as a data scientist for a large oil company. She's making £200,000 a year. All she does is prepare a PowerPoint presentation every week, and she's utterly bored. And that sort of low level of productivity is something that I definitely share that feeling of just feeling totally constrained into what I'm actually capable of doing. And a big part of the problem is the managers and the infrastructure not being set up to allow this particular person to do anything useful or interesting that would make them not bored on a daily basis. But then there is also a slight responsibility from us as data scientists to make the managers aware that this is a big problem. There's something really badly going wrong here. Here's another quote. This is from Georgi Georgiev's book, Statistical Methods for A/B Testing. He said, this is coming from a company that he worked with. He actually did a meta-analysis of their A/B tests and found they were severely underpowered given their designs. We recently stopped A/B testing. We ran more than 70 conversion tests before making this decision, and we had only 3 significant winners. And to me, this is a real indication that whoever was running these experiments really didn't know what they were doing, because 3 out of 70 is just far, far too low. So probably indicative of an underpowered problem given their designs. But the other aspect of it, which I think is underplayed in this, is that if you are not implementing 67 of ideas which probably had questionable, at least questionable, benefit to your business, then that's positive. And that's part of the reason why we do experiments in companies. So there's clearly a problem in that company of ineffective application of data science. And then this is a quote from one of my friends who works in a very large games company, was successful in spite of the senior leadership team's decisions. And that to me is indicative of poor decision hygiene. This company, they have a pretty significant data science team. They have data analysts, data scientists all working on this. Most of what they do is actually financial reporting, believe it or not. And the lesson here is that, the point I'd like to take away from this is that if you're one of the lucky companies that has the luxury to be able to just waste the resources of a team of 5 data scientists and data analysts, then good for you. But most of the companies I've worked in are not in the same position. So something has to change if we're going to make use of that resource. So that's sort of 3 sort of areas where I'd like to sort of highlight some problems: productivity, ineffectiveness, and decision hygiene. But I think there's actually something more fundamental going on here about the root cause of these problems. And it's a complex problem, and it's not exclusive to data science as well. I think the software engineering industry is struggling with this as well. And if you were to talk to an economist, they might say something like, oh, low interest rates made it easy for us to hire a load of useless people. And I think there is some truth into that, but I'm going to claim that there's another contributing factor to this, and that's that we just really haven't stopped in our short history of data science to actually think about the foundations of why we do things, the approach we take. And I think doing so actually has some benefits to, in not just some sort of intangible philosophical way. And the point that I'd like to make more specifically is that if we think about the types of knowledge that we're working on, the types of analysis that we do, I think is actually in pretty rocky territory. And the philosophical technical name for that is epistemology. It's the philosophy of the knowledge that you acquire. And I think we can highlight this problem actually by just considering the name, data science, because I don't think it gives us the right impression of what we should be doing and how we do it, when we're working effectively, how we actually do it. So I don't think we're scientists. Fundamentally, I think there's a massive difference in what we do compared to what scientists do. Science is about acquiring sort of knowledge of the immutable laws of the universe sometimes, and it's expressed in theory, and they invalidate their theory progressively through experimentation. And I have no interest in theory whatsoever. I have no interest in some theory of data. What I'm interested in is actually solving problems and being effective for the company I'm working at. So I don't think that term is helpful. And from thinking about this problem, it's clear that we're actually engineers. And I think this particular definition of engineering makes that absolutely abundantly clear. Engineering is the use of heuristics to cause the best change in a poorly understood situation within the available resources. I absolutely love that definition. It sounds exactly like my work when I'm doing something effective. Heuristic here means just anything that is a plausible aid or direction in the solution to a problem. And that seems to me more like what effective data science actually sounds like. And the other problem I have with the name data science is that data are particularly uninteresting to me. Unless you're a statistician trying to produce a new statistical model or distribution for which you hope to get a promotion, then I don't really care about data at all. What I actually really care about is doing something useful for the company I'm working in. So 2 parts of our name seem totally inappropriate for what we're actually doing. Now, I propose that a closer name to what we actually do is decision engineering. I'm not saying that we should adopt this or that it's a good name, because I think there's some redundancy, because engineering implicitly says something about decision making. But the idea where I'm sort of saying what we really do is more like decision engineering is because it makes our goals explicit. And if you were to hire a decision engineer, whatever that would look like, that person's there to help you to clean up your decision-making process. And that's their sole job. So if you try and get them to do useless things like we tend to get some data scientists to do, they can kind of say no, because that's nothing to do with decision-making. So that's really kind of the underpinnings of the talk, or the rest of the talk. And what I'd like to move on from is all the sort of pie in the sky, like fluffy stuff, is the useful stuff, i.e. the things which I think are effective tools that I found in my career for doing this decision engineering thing that I'm sort of loosely describing here. So I'm just going to list them all off and talk through them, and I hope I don't lose people along the way. But I hope that at least one of them sticks in your head. So so I should explain here. There are heuristics, and there are also rules permeating these heuristics, which try to sort of group together the heuristics in some way. So the first rule is to understand people. And the reason why I've put that at the top is because data science is typically thought of as about understanding data. And I actually think that the much harder and the more fundamental problem is understanding the problems that people have with understanding data. And if you've read anything by Daniel Kahneman, you will know that we are not statistically literate thinkers. myself included, struggle to think statistically about problems all the time. And understanding that and keeping that in your head at all times, well, keeping it in my head anyway, has proved to be incredibly valuable to helping navigate the path of effective decision making. So one of the things that I like to do is use toy models, and we'll go over that in a moment. And the reason why that's helpful is because it makes it absolutely apparently clear what is scary about a particular problem or what they should be aware of. So a corollary of this rule is I think all self-serve analytics should be banned. I think that they are so utterly dangerous. It is a way of putting into the hands of anyone in your organization uncontrolled observational trials, which you can just use a mouse to drag and drop them. I've never seen anything good come of it, and I think it totally works against all of the problems that we have with statistical thinking in our brains. It seems to me like they've actually been optimized to make that worse. Because they've simplified them, they've made them more user-friendly. It actually makes them less robust and less useful in practical terms. So I just think we should ban them. And if someone above you wants KPIs and all that sort of stuff, have some sort of set cadence with which you will discuss them, and you will talk with them so that they can't look at a line and then it peaks and then they go, oh my God, what happened then? And you go, well, it's just noise. So we want to avoid those situations as much as possible. Something which I would suggest is a better way of thinking about decision or making decisions, beside self-serve analytics and dashboards and analytics tools, is something which Daniel Kahneman mentions in his last book, Noise, called the Mediated Assessments Protocol. And I won't go into really great detail about what it actually entails here, but the fundamental idea is that decision-making should come after all of the evidence has been evaluated. And in particular, not just decision-making, but discussion. Because one of our biases in decision-making or thinking about problems is that we like it when people tell cohesive stories. And cohesive stories may not necessarily be a good representation of reality. And so in the Mediating Assessments Protocol, effectively what you're saying is, we're not going to discuss anything, we're going to present all the evidence in as cold, quantitative way as possible, and then we can chat. So that any particular biases you may have had have been at least mediated to some degree by the quantity of evidence, potentially against what you think is the right answer. Kind of in line with that idea as well is this idea of falsification. Falsification is we'll all be familiar with from the scientific method developed by Karl Popper. This idea is that in science, you can never verify anything, you can only ever falsify anything. And so this is incredibly valuable for us as data scientists, because if we see that some of the assumptions in our business are non-falsifiable, then we have a problem. And we need to frame them in a falsifiable way, because then we can collect evidence to try and falsify those assumptions. So in terms of something more sort of specific on the idea of falsification is about the tails of distributions. And in particular, what I'm thinking about here is that there are different worlds or different families of distributions which are admissible for a particular data set. And being able to falsify that the data generating process for this particular data set is in one particular family is very useful, because it means you don't have to think about all those ones. And you can focus your efforts on managing the risk of another one or another family. So who here has done a plot of some data and seen something like that? For years and years, I would do this. I would plot a histogram of some data, and I'd get something like that and I'd go, oh my God, what do I do now? I literally have no idea what to do now. And what I'd end up doing is I'd probably be like, okay, well, let's just squash the x-axis a bit. And then you get exactly the same pattern again. And so it was only recently, probably in the last 5 years, that I came across the ZIF plot, which, for those who are familiar with it, is on a log-log scale, you're plotting your realizations of your random variable versus the survival function, the empirical survival function. And this is exactly the same data as this, but this tells you about some structural relationship between the data, which is totally non-evident from the histogram. This data is generated from a Pareto distribution, which may not be a particularly useful model for the entirety of a distribution, but certainly in the tails, using goodness of fit tests for the tails of data following a Pareto distribution absolutely changed the way I think about data, because you can rule out that the mediocristan world, as Nassim Taleb would call it, i.e. the normal world, things like weight, BMI, the things that are constrained by reality, doesn't apply. we're in some extremism world where we have to think about outliers. We can't just explain away like the outliers on a box plot by saying, oh, we can exclude those, because they're the actual information. That's where the information lies in this type of data. So with something like a zip plot, it allows you to make a falsifiable claim that certain distributions are not admissible for my data, and then I can focus all of my attention on a distribution or a family of distributions which are more viable. And so collecting all these ideas together in a more sort of Nassim Talebian way is a principle of anti-fragility. For those of you who aren't familiar with this idea, in his book, Anti-Fragile, he puts forward 3 categorizations of objects or things. You have fragile objects, those which are harmed by disorder or rare events. You have robust objects, which are fairly resistant to rare events or extrema. And then you have anti-fragile objects, which actually benefit from those. And so if, for example, you find that your data is Parisian in the tails, figuring out ways that you can benefit from that is a principle which I found really useful over the years. And I think a prime example of companies who managed to do this really well are mobile games companies, a few of which I see in the audience. I was astounded in probably about 2017 when I was having a chat with a mobile game developer in Brighton who explained their process of developing ideas. Now, this may not work nowadays, but it certainly did back then. Someone would come up with an idea of a game. They would immediately go to Facebook and generate ads for that idea and a landing page. And all they would be interested in is the conversion rate from the ad to the landing page. And if it didn't reach a certain bar, they would can the idea straight away. There would be no further development on that. It's dead. If it met the bar, they would then have a skeleton crew of an artist, a designer, and a programmer putting together an absolutely rubbish prototype for that game. And they would again see if they could get users to convert to monetization. And if it didn't reach those thresholds, there was no further development. And so maybe implicitly, there was a understanding of utilizing the tail as effectively as possible. If you know that only a small fraction of games are ever going to be successful, you want to be exposed to as many ideas as you possibly can. And so that development cycle was the most effective way for them to be anti-fragile. A corollary to this rule of being anti-fragile is I highly recommend that you avoid prediction tasks as much as possible. There are companies that clearly are able to do this well in some way, but I have never once built a useful predictive model. If I look at how well it does above random, it's typically like 10%. And even if you say that's useful, I don't think we put enough effort on thinking up front about the risk reward of a particular model. Because as soon as that model is live, it's creating this feedback loop over your data where you have to then do proper testing to make sure that you actually have a decent control group if you're going to do odd modifications to that model. I think there are much more effective ways to utilize our resources apart from just building some model, which gives you a point estimate. And one of those types of tools is the next heuristic that I'd like to discuss, which is extreme value theory. So I'm not sure how many of you here are familiar with this particular idea. It was first introduced in the 1970s by Dutch engineers who wanted to build flood defense systems. And because Holland is very flat, and so they get flooded all the time, so it's something really important. And they looked at the way that the Japanese engineers had built their flood defense systems, and all they did is they said, oh, this is the maximum that we have observed, so let's just build it as high as that. And that leads to disasters, as if you know anything about Japanese history, will be self-evident. And so extreme value theory is basically the statistical theory of maxima, and what you can extrapolate about the maxima of a distribution from the maxima of your observations. And we're actually able to use this pretty effectively at the company I work at now, GOS, with our share referral system. So we had a system in our game where if you shared the game with someone else, you could get in-game currency. Both of you got in-game currency. And that currency at the time was enough for you to actually redeem a real-world prize on our store. And what happened was there was one particular girl who had a decent following on social media, who probably did something, we never confirmed this, but she probably did something like message all of her followers and said, hey, download this app, take my share referral link, and we'll both get free stuff. And so what happened, she got an enormous amount of coins, our in-game currency. I think she got something like 200 referrals, maybe even higher, I think, looking on this. This is on a log scale, but it was astounding because we'd never seen anything like that before. And so basically what I did is I fit a generalized extreme value distribution to our data and found that, yeah, it was totally predictable that we would see someone who had that many referrals. And that not only that she was probably only in the top 1%. So if you had 100 users who referred, she might be in the top one. Might be the top one with 161 referrals or something like that. But if you had 1,000, they might have 769 referrals, which would be worth about 20,000 of one of our expensive in-game currency. And if you had 10,000 of them, that would be worth about 20 grand's worth of prize. No, sorry, not 20 grand. About £1,000 worth of actual prizes. And so just by thinking about this way, thinking about being exposed to risk and exposed to the distribution which was generating this, our data, we're able to say, we need to stop this because this is not something that we want. And so we changed that mechanism. Moving on to a slightly different rule, but something which I found incredibly helpful as well, is to make explicit our utility function of the business. And that can be of a particular project, or it could be at a high level what the strategic goals of a company are. But unless you make this explicit, there's no way that analysis can actually make sense. Because without the context, there are so many things that you could say that explain away data or explain away analysis. So you need to focus on in your analysis and be thinking about it all the times to make sure that when someone comes and says, well, I don't think this is right because we're not like that, you can say, well, this is the reason why this is applicable for our particular scenario. And following on from that is the idea of risk-reward evaluation. Because I think it's very easy to present the reward of particular ideas. I think this idea might work because it will entice people to come back. But we don't focus enough on the risk side of things. There's always risk involved in every decision, every change that we make to a product. Whether that's risk in terms of development time, the cost of having to maintain a particular intervention. And especially in A/B tests, I've had scenarios where just by considering it in terms of a risk-reward framework, you can invalidate a lot of ideas even before doing the A/B test, because you say there's no way that we could get the uplift that we would need to see to make the risk of this particular intervention worthwhile. And mentioning A/B tests, there's something which I've come across within the last few years, which I think is a superior way of doing A/B testing, and that's group sequential A/B testing. The idea behind group sequential A/B testing is that we really want to peek at our data because we want to stop failing experiments early and clear winners early. But if you just have a standard A/B test, the design is not that would break the design of your particular test. So group sequential testing is designed to allow you to effectively do early analysis of your data, and as represented on here. So on this graph here, we have cumulative sample size. We have our test done on the red dots. And the idea is here, we do this evaluation at some point before we would have done it normally. If we cross these two decision boundaries here, we can either accept the null hypothesis or reject the null hypothesis. And in doing so, on average, you will have dramatically more efficient A/B tests than you would have done before. In the worst case, you will have less efficient A/B tests than before. But especially if your design of your test is something like strong superiority, so the intervention or the alternative has to outperform by, say, 5% or something like that, like a quite stringent sort of design, then this can actually cut down the amount of your sample size for experiments quite dramatically. So look into it more would be my recommendation. Moving on to the next heuristic, simulation. So here I mean any tool where you are, simulation, where you are essentially taking historical data or doing some form of modeling to help you build intuition about the type of problem that you're actually faced. And I would categorize those into two different, I would say there are two different categories which I primarily use for simulation. And one of them is mainly probabilistic, and one of them would be like a bootstrap Monte Carlo type simulation. So I've got some examples of those here now. At GOS, we were looking to, apologies about the contrast here, you can't really see the DAG, but there are lines. Hopefully you can kind of see them. We were interested in an intervention, a new mechanic where the user would run out of energy. So after they played 5 games in a row, they'd be told, hey, you've run out of energy, so you've got to stop playing. And the idea was that it would encourage users to come back and improve the number of sessions per day, for example. And so if we sort of isolate that kind of the user's behavior around that point, they've just played 5 games, so they're sitting at the top left vertex. And they've got 2 choices. They can stop playing, or they can play a 6th game. And if they stop playing, they can either come back and play that 6th game, or they can churn. And so this out-of-energy mechanic, if any of you are familiar with the language of causal inference in sort of Judea Pearl's sort of formalism, the out-of-energy is effectively applying a do operator to the stop playing vertex. It's forcing all users to go through stop playing. And you can just trivially see that if the probabilities of transitioning from stop playing to 6th game and churn stay the same, that just by piping more users into stop playing, you're going to increase your churn rate. And I estimated that it would actually increase our churn rate by about 7% relatively, which is a considerable hit. So even if this particular mechanic does have some benefits to quality of users or something like that, improving session lengths, if your utility function says that we really value retention and that we need to keep our retentions high, you have a massive hurdle to overcome before you can, this particular mechanic can be effective. And here's an example of a sort of more traditional Monte Carlo bootstrap kind of simulation where there was an internal discussion between my CEO and my sort of head of product and myself, where they were saying, hey, Tom, these experiments you're proposing are too expensive. Can we just do it quick and dirty? And can we just like not do the A/B testing? And I was like, well, I'd much prefer if we just did like high type 1 and type 2 error rate experiments or A/B tests rather than do nothing at all, and sort of help evaluate what that would be like if we did that. You can just bootstrap an analysis of, okay, what would happen if we did 12 experiments? Let's see what happens. And in this particular case, the nice thing about bootstrap, of course, is that you get statistics across the whole spectrum of simulations. So in this particular case, you can see that no testing would actually leave you in a worse place off than if you just did like kind of bad testing versus, I don't mean bad, I mean like high type 1 and type 2 error rates versus being really safe and having like really like 5% alpha and all that sort of stuff. So I would say the overarching theme in all of these, in everything I've presented here, is to really understand your tools. And that's kind of the heart of, I think, an effective sort of decision engineering methodology, is that everything, if we don't really focus on the actual things we're doing, when they are useful, when they have problems, when they're appropriate, when they can actually solve a particular problem, then we will fail more often than not. And I think that's a prime example of that is, in this thinking about distributions. And if we don't think about distributions, then we are exposing ourselves to a huge amount of problems. That's not to say that if our data is admissible for a normal distribution, then it's a good idea. But making that consideration without rushing in is a primary point I'd like to get across here. And a corollary of understanding tools, which is perhaps maybe seem like a bit of a blindsider here, but I'm also banning Python. And I'm really sorry that I'm going to hurt people's feelings here, but I'm really not that sorry, because Python is just a really bad tool. And it just fundamentally doesn't allow you to write efficient code. And something that I think I spoke about at the beginning is productivity, low productivity. I think Python is like one of the biggest productivity killers that I could possibly think of. It doesn't. If you ever want to optimize any code, it's like, no, you're not going to do that. Line profile is awful. So please just use R or Julia, and let's just put this in the past. So that's basically everything I wanted to say. Here's a little rundown of sort of the methodologies that I was describing here in a rather haphazard, rushed way. I have some honourable mentions as well, which I would really like to talk about, but running out of time. So propensity matching is something that I have found hugely beneficial, and potentially not in the way that it's typically done. Keeping in mind falsification, again, I use propensity matching to falsify that there could be a causal effect between two variables. I'm not using it to say there is a causal effect. I just want to invalidate that idea. And in particular, if you're thinking about like a causal graph, it's like, let's block off the back door between these two things and see what happens. And then if it does appear from the propensity matching that there is, then it doesn't mean there is. It just means that we should test it. It's good evidence that an A/B test is appropriate. Next one, as an honourable mention, is process mining, which, for those of you who aren't aware, the idea of process mining is to produce models of event data. I think a lot of us in this room will be dealing with event-type data, especially if you're in the games industry. And most of our methods are about aggregating that type of data. And process mining is probably one of the only methods that I know of that puts the event aspect of our data sets really first and foremost. And I actually used this year to identify that 100% of our Android users at one particular point were getting booted out of the login process, and it had gone unnoticed for like months. And that was just simply by doing a segmentation on the process models of user data. And then the last one is the Pareto MBD model, which might seem a bit weird to be talking about a statistical model because it's a very specific one for customer lifetime. But it's the only model that I've ever come across which actually has given me some useful insights into the data generating process of the way that users churn in a product. So worth having a think about. Okay, and then the rules, just to summarize them: anti-fragility, write down your utility function, understand people, etc., etc. No Python being the primary one. Okay, so to wrap everything up, in a rather rushed way, I've tried to present a slight modification to perhaps the way I think about data science, and hopefully something that might modify the way that you think about it as well. I think the idea of focusing on decisions is an important one, because if we're just thinking about manipulation of data, it's not necessarily tied to the thing which we really care about, which is making effective decisions or being a useful asset to a product. And then so the techniques that I proposed are something which I fit inside my head as the tools that I go to help make effective decisions. And I hope that there's been some utility in those for you as well. And that's everything I have to say. Any questions? Sam?
You're banning Python. What else do you ban? I have a sneaky suspicion there might be some other things high up on the list. Throw in the ring.
Oh, I'm struggling to think. I mean, there are plenty of programming languages which I think are useless. So yeah, absolutely the analytic types products. Everything in that regard are pretty useless. I can't. What are you thinking of specifically, Sam? I feel like you know me. Oh goodness. I think most models. Yeah, my experience of most of the machine learning type models is that they are people don't understand the assumptions behind a lot of these models. That I mean, it's so easy to just run model.fit in so many applications without really understanding what a random forest is doing, or what XGBoost is doing. So I would say these things are probably have their place for some organizations, but I wouldn't ban them, perhaps, Sam. Hello.
So everything you said, I believe some people will echo, but how do you educate your business stakeholders about a lot of things you talk about?
Sure. So the question was for the audience that the lady was saying that she echoes some of the sentiment, but her concern was how do you actually educate people in the business? And I suppose this is quite easy for me because I have no problem in telling people what I think. But I think honesty is actually key to that relationship. It has to be you saying up front, this is not a useful thing to do, and being able to clearly say why this is not useful. And if you can provide evidence with simulations that this is not a good idea, I think that's helpful as well. So that's the reason why I've kind of put that in heuristics, because quite frequently having some form of data to back up what I'm saying is valuable. But again, it's a communication thing. And I think making any sort of program is more valuable than the status quo, essentially. So happy to talk about that afterwards if you'd like. Sorry, I've meant to be letting people get to the microphone.
Thank you for your talk. You mentioned that one of the, I think it was a rule, was not to use any predictive models. And I have to say I've used predictive models quite a lot, so I'm wondering what your suggestion would be to replace it with, or what, if you have a prediction task and that's a business case, how should you approach it then?
So I think if there is a valid business case for a predictive model where the risk-reward analysis has been done properly, and you can justify the model and you've thought about the feedback loops that will inevitably occur from implementing that model, and a point prediction genuinely is valuable, and you're not exposed to the consequence of tails, then you can predict. But that's a lot of hurdles that you have to get through. So my approach or alternative would be to say, okay, how can we benefit from rare events? Or how can we make sure that we are not exposed to rare events if, for example, our model goes wrong? Because these models will invariably have problems in them. You know, I mean, I worked with a company a couple of years ago, and the data that they wanted me to forecast on had loads of stuff, was data through COVID. So what value is that going to be if, for example, I had built that model a year before COVID? It's not going to work. And that company would have been totally exposed if any decision-making had been based on the results of that model. So again, it's more about how can we frame the decision-making process so that we don't have to make predictions. We can think about 5% risk, value at risk, or something like that instead. Any more for any more?
Thanks for the really good talk. I was wondering if you kind of agreed with the idea that there's this trade-off between amount of stuff we do and the quality of what we do, and whether you think there's just too much quantity. People are just doing too many things rather than doing good quality stuff, and how do we stop from just doing model.fit and just doing as much as we can? And yeah, do you agree with that idea? Too much being done rather than useful things?
I do think that there is a tendency to just think that by looking at data or producing analysis on data that you will find something useful. It's kind of like the idea behind mining, and I think there are places for data mining, but it's usually overdone, and that is quality over quantity, certainly. It's very easy to produce analyses of data that are completely unrelated to any decision-making process. And so if up front there is a consideration of the actual problem and the decision that a piece of analysis is going to be tied into, if this is going to decide if we're going to do this A/B test or not, or this is going to decide if we if we make this business decision, if we partner up with this particular other company, then you will never go astray because your analysis is absolutely tied into that. Now, you're probably going to be spending longer on a piece of analysis, but there's less waste. There's less waste in the whole system. So I would totally agree that quality over quantity is fundamental to this kind of idea I'm proposing. Phil.
Hey, Tom. Thank you. That was a lot of fun. For someone who claims, that data and science are inappropriate labels, you seem to be very eloquent and have a lot of ideas and care deeply about both those two topics. My question, I guess, was about the loathing of self-service analytics, though. Given how hard it is to recruit talented data scientists, how do you enable your company to make data-informed decisions if they have to come to you for everything?
I see the point. I think the focus, as with the last question, I would put it more towards reducing the number of analyses down to the absolute crucial one for decision making. Now, in an organization like King, there are a lot more decisions being made because I suppose you're running probably hundreds of thousands of A/B tests every single year. And so you need people to analyze those things, but they're directly tied into decisions. So that is something which you can justify. I think, given that there is a limit of talent, I think you just have to say, within the constraints in an engineering framework, that we can only answer these problems. And in doing so, it focuses the business on the most valuable types of problems that you need to solve or decisions that need to be made. And the other things, which may be more explorative or more experimental, kind of fall by the wayside, and maybe necessarily so. But I would argue that the benefits of those things being somewhat sort of fat-tailed in a way is probably negligible for most of those things anyway, if that makes sense.
Sometimes definitely encountered situations where someone who's just genuinely curious about data has kind of like played around a dashboard and found something that was just horribly broken, obviously, that, there's definitely value in people kind of engaging with data, coming and talking to you about, but maybe not necessarily making decisions.
I definitely get that. So I think I did a post on LinkedIn about this the other day, where one of the rebuttals I get about self-serve is finding broken things. And I would say that you can find broken things by alerting. If something, and that's more efficient use of time. But I think there's a certain amount of silent evidence in that particular case where people can say, or people have said to me, hey, but this one time this one guy found this really useful thing, And because you don't see the silent evidence of the analysis which led to nothing or led to a spurious correlation being pushed into production, because you don't hear about those things, it's difficult to evaluate the risk reward of that particular thing. And I'm coming down hard on the side of it's too risky. Any more? Apologies for the sound issues. It sounds a bit spotty to me, but okay. Thank you very much, everyone.